The NASA Astrobiology Roadmap mission of better understanding the origin and the composition and the distribution of life throughout the universe, as well as what life might hold in the future, has been the template driving NASA missions for many decades. And the U.S. space program has focused on this by first sending up flybys and orbiters around Mars so we get a good detailed understanding of what the surface of Mars looks like, as well as some basic geochemical and geological analyses. Now the next generation of those missions is to have these coupled lander, rover, and orbiter missions in which we actually put robots on the ground, allow them to go around to collect samples and take close-up photography, as well as do some chemical analyses, and then use the orbiters to help with the imaging and then return those images back to Earth. Lander and rover mission sequence has been extremely successful, and it's resulted in multiple levels of understanding better the question of, has Mars been habitable in the past? The question is not about in the modern day, because Mars is a very harsh, extreme environment, 180 degrees Fahrenheit swings in temperature every day, low gravity, very thin atmosphere, a very harsh and difficult place to be at the moment. But the big question is, was Mars habitable in the past? The next question of detecting life is going to be on some of the upcoming future missions. So the rover missions laid that groundwork for the habitability of Mars in the past. And one of the first missions that was very successful was the Viking 1 in 1976. And Viking 1 was a lander. It was not able to move around on the surface, but it collected all kinds of up-close photography and chemical analyses that have been pivotal for sculpting and molding the rest of the mission since that time period. In 1996, another very successful lander called the Pathfinder was put on the planet, but in this case that was able to move around. It was a rover that had a coupled lander station, and again was all linked to an orbiter. But what I want to focus on now are two of the more recent missions with rovers, and that was the Mars Exploration Rover sequence, which included the Spirit and the Opportunity rovers. And then as we speak, the Opportunity rover is still operating, but then in 2011 we also sent up another mission called the Mars Science Laboratory, and that's the Curiosity rover. So I want to briefly look at what this has yielded us in terms of a vast amount of information. And it's important to consider that the rovers and landers have been placed on widely distributed sites around the surface of Mars. So we've had some very distinctly wide geographic coverage of where we're getting this information on the planet. So the Spirit and the Opportunity rovers both successfully landed on Mars. Unfortunately, after the initial parts of the mission, the Spirit rover stopped communicating with Earth. And so there were technical problems. Also, it had to do with the very harsh conditions of a Martian winter. And so we no longer have contact with Spirit. But Opportunity, on the other hand, has been just the opposite. It's a remarkable sequence of events. The rover's been operating now for 10 years, and it's also covered about 24 miles of distance, which is phenomenal. Both the duration and the distance covered are far beyond the expectations of the original space team. These were these were robots that were actually on the order of about 2 to 3 feet in length, relatively small. And they had small tractor tires and wheels that moved them around. And they weighed upwards of about 400 pounds. The Opportunity rover does have a whole variety of equipment, the capability to do some very detailed geochemical analyses, mass spectrometry, and other techniques to tell us what the chemical composition is of the rocks and soil materials that they collect. But it's also been able to have extremely high resolution photography as part of that as well. The Opportunity rover was originally put down at Eagle Crater, and then it moved to Endeavour Crater, and then now it's moving beyond that to Greeley Haven. So it's traversing upwards of 24 miles across the planet. The 2011 mission of the NASA Curiosity rover. The NASA Curiosity rover is about 2,000 pounds, so it's 4 times heavier. It's the size and weight of a small car. It's significantly larger in terms of its payload that it carries. It has much more sophisticated geochemical analyses and spectrometry to understand the chemistry of what's happening, but especially important is that it has the capacity to drill very shallow holes on the order of 1 to 2 inches in depth. And so that ability to not only collect samples but drill holes and then collect powders as a result of that has been very important. Another instrument on the rover is that it has the capability to laser blast the surfaces of rocks. So therefore, any kind of weathering that occurs on rocks that the rover encounters, it can be blasted off, and then the chemical analyses and visual analyses of those rocks can be completed. Another thing that's important about the Curiosity lander is that it represented a completely new version of how to get the spacecraft onto the planet. Earlier versions of the rovers actually had parachutes and a whole series of balloons around them, which allowed them to land and bounce and eventually come to rest on the planet, but that's pretty hard on the equipment that's on board. So the Curiosity lander had a very sophisticated series of rockets and parachutes, and then be able to have the rover be very gently lowered from a rocket booster that hovered above it. And the landing site for the Curiosity has been the Gale crater, and it successfully completed analyses across a large traverse within that crater sequence. And one of the things that's been remarkable about the combination then of the rover missions, both the Opportunity and the Curiosity, are the following: that first of all, we have been able to definitively prove that there were extremely large volumes of water on the surface of Mars in the past. This is primarily a result of having layered sediments. The Gale crater was chosen because the Curiosity was laid down in a stream bed, and then that was adjacent to an impact crater. And then from the stream bed now, the Curiosity is traversing up to the middle of a peak, a mountain peak that occurs in the center of the impact crater called Sharp Mountain. And so the whole concept of has water been abundant on Mars in the past, that's been definitively proven by the sedimentology, the composition of the grains, and their geomorphic physical distribution that we see on the surface of the planet. Another very important part of the Curiosity mission has been to have close-up visualization of what the actual rocks look like. And these are, the majority of these are sedimentary rocks. They're composed of grains of sand that have been transported and moved from either water processes or meteor impacts. And importantly within that, we've also been able to see that those rocks are heavily fractured. And inside those fractures, we had waters moving in the shallow subsurface of the planet, and they fill those fractures with minerals that are very common both on Mars and on Earth, including the mineral calcite. So the proof that we had water is critical to, as a resulting feature of that mission. Now what the Curiosity and the Opportunity are focused on is what is the more holistic view of the habitability of Mars in the past.